We have 3 more seconds. Param, could you please close the door? We assume that the quorum is here. So, okay. Let me remind you where we are. So if we wrote the code successfully, which allowed us to find the smallest and the nick, the door. Thank you. To find the smallest and second smallest. And while I planned to demonstrate that it wasn't stable, I just asserted that it wasn't stable and asked you to find a way of making the code stable. Who did? That's very impressive, guys. The guys who didn't do it should feel deprived. Okay, and what we're going to do, we're going to see several ways of doing it. Believe it or not, the problem possesses multiple solutions, all of them very instructive. So, as a matter of fact, what I'm going to do before we go through the code, I'll tell you all the algorithms which we are going to cover today. And then we will implement them all, and then we will even experiment with them. So, obviously, since I want to do 4 algorithms, the likelihood of us doing it with the old methodology is not going to work. So I have to speed things up. Okay, so first of all, why was our thing not stable? If we look at our algorithm, the problem was in this little piece of code right here in front of us, which was doing this operation min1, 2. Because what this operation was doing, it was doing combine yx and combine xy. And while swapping the thing, it was doing something terrible. You see, all of our binary counter machine was very carefully written so that the order is preserved. We used associativity, but never commutativity. And here we go and swap. The moment we swap, all the information about the order is lost. And roughly speaking, how often, what does it result in the final list of people who lost to the winner? They roughly go 50-50. Some come from the left, some come from the right, assuming random distribution of the things. And they're sort of intertwined. So it's basically impossible for us to restore the original order. It's lost. So the first idea, of course, is that even if the order is lost, couldn't we derive it from the iterators themselves? And the first algorithm which we are going to come, it says, let us assume that on these original iterators in our range, there is an ordering relation. By the way, what does it mean? What kind of iterators have ordering relation? Random access iterators, right? This is the concept which has ordering, because forward iterators do not. If you think about it, if you have single linked list, figuring out which pointer is before which pointer is not doable. Well, if they're random access, the operation is defined, and we could use it, and will use it. So, and a fairly trivial modification of our algorithm would allow us basically to make it stable, right? But then, of course, somebody like Ryan would come and say, well, but there are iterators which are not random access. This is much less general. What could we do? And of course, now after we figured out how to do it with random access iterators, it's fairly trivial to change our algorithm to make it work for any forward iterator by attaching to every iterator which we put into our data structure its index, right, which would allow us to compare them. Nice, nice. But, guys, in reality, both of these solutions is an overkill and would do extra things which are not necessary. Why? Because if we carefully think about our original algorithm, we could slightly modify this thing where we add things to the list of losers. Let's imagine the situation that instead of having one list of losers, everybody is going to carry two lists. Lists of guys he defeated from the left, and the list of guys is defeated from the right. Right? So you know when you play the game which way it's going. So it's very easy to arrange it. We shall see in a second how. So if we do that, then all the guys to the left will actually be positioned in exactly the order they lost. They sort of, since we're going to be pushing things to the head of the list, and every guy who comes from the left is going to be further and further and further away to the left. If you think about it, when you play in the tournament, the guys with who, if you play with somebody and you're on the right-hand side, the guy who you play on the left is going to be further away from you than all other guys whom you played on the left. And the same thing is true for the right guy. So therefore, anybody follows what I'm saying? Ryan, are you with me? Ryan is with me. So you have to actually think about it, but it is so, right? Because further out, as you go up the tree, you're always playing the guy who is 2 to the I steps away from you. Therefore, he is further and further away with you. So you are going to have now two lists. One list which is going to go in the natural order, and another list which is going to go in reverse order. But after we're done, what could we do? We could simply find the smallest of this list and smallest of that list appropriately. Here we have to be a little careful. And then compare them. And that is going to be the second guy. Now we just build all this complicated machinery, and it's all very beautiful. How practically significant is it? This is sort of Nick keeps bothering me. Why do I need to know this stuff? Well, first of all, you need to know this stuff because it's beautiful and good. Okay? But then sort of it might actually be practically useful as it is if you ever need to play a tournament, determine two guys, and the comparisons are very, very expensive. What if they're not expensive? Could we do something faster? And this is the final algorithm. So we already have 3 algorithms we need to do today. So this is the final practical algorithm. So very often, things come in random order. Right? They're just random permutation. And you want to find the largest and the smallest and the second smallest, the winner and the runner-up. So what could you do? Let us come with a very naive and simple algorithm. Let us do the following. Let's assume that we already determined, we came to the position I, and we already determined winner and runner-up up to that point. Then we could go one step further by doing the following thing. We could play the new guy, the new candidate, against the runner-up. Everybody understands that we should never play him against the winner. The idea is very simple. Here comes somebody, he's too unimportant to play against the winner. First, he has to defeat the runner-up. If he defeats the runner-up, then we will let him play the winner. Make sense? Now, what is the likelihood that he is going to defeat the runner-up? Could we estimate? We actually can. Bert tells us we can. Would you like to estimate? Ith guy. In random order. 2 chances in I. Very good. So 2 chances in I, which means that somebody, the blue, what's over there? It means that it's 2 over I, yes? Let's assume that they're distinct. So now, if we do from 1 to n, how many times are we going? Obviously, we're going to do one comparison playing against the runner-up. So we're going to do n comparisons, or n minus 1, actually. But that's plus the sum of 2 to the I from to 2, let's make it 2 to the, actually, let us make it like that. 1 to n. I just borrowed one from this guy. Right? What?
It's not till you get to the third guy that you have to play against the runner-up.
Well, the important thing, it's really not important, because this n is going to infinity eventually. So let's not worry about that. Right? What is it equal to? This is equal, again, something like n minus 2 plus 2 times sum of 1 over I. Anybody knows what this thing is going to be? This is a wonderful harmonic series. So what it is, finally there's some use for analysis. So this thing is going to be n plus, no. This is harmonic series converges to something roughly equal to natural log. That's the remarkable part of it. Right? This guy Euler, some of you who took the previous class heard of him, proved that it's actually equal to, in this particular case, 2 log n, natural logs of n, plus something which is known as an Euler constant, and plus O of 1 over n squared, which means something very small. Right? And if it's very small, we could just get rid of it and replace this with approximately. So this much, much simpler algorithm is going to be almost as good as our optimal algorithm on the average. Right? We're trading one binary log for two natural logs. That's not a bad trade, especially considering that we have a linear factor. Okay. To give you an idea, by the way, just let's do things in a little bit different order. If we go here, and if we compile our code, clang plus plus minus O2 min.cpp. By the way, I will in a second push the code so you could see it. I forgot. I apologize. Out. What we see, actually, I don't know what I do. It's now the practical algorithm, which is the last, actually is even faster than the optimal. Let us see why. I probably left it. It's all Jack's fault. I left it in imperfect state. Where did I leave it? Yes. I told you it was all Jack's fault. I'll explain. We will have to put them back in a second. Ryan? Oh, it's happened? Everything is up to date. How could it be? Git. Commit minus -a. What do I say to avoid dash m? And okay. Now it's a git push. I apologize, guys. Why does it take so long now? I do not understand. Are we going through wireless? Yes. Okay, so let us now do clang plus plus minus O2 min dot cpp and dot a dot out. Okay. Now it's a more plausible thing. Right? So we're doing, by the way, we're doing million guys. So the optimal guy, and we have 4 versions of optimal guys, does 1,000,018. That's the log. And the practical guy does 1,000,028. It's pretty good. It's pretty good. However, again, this is expected number. It could get much, much worse. What is the worst case for the practical guy? The reverse. Right? Let us quickly test this conjecture. If we go to min.cpp, and instead of giving it random iota, we will give it a reverse iota. And then we go here, and when we do this, then we do this. Observe that our optimal guy is faster. Why did it happen? How could it be? You see, our practical guy is no longer practical. I mean, with double, somebody was predicting n minus 3. Yeah, we got n minus 3. Yes, exactly right. So, but now, how come this dropped to 10? How could it be? Is it a fluke? You see, our tree is not perfectly balanced. It has these little things on that side, on the right side. And now, our small guys are on that side. So the guy who won is in an unbalanced or not perfectly formed subtree. Therefore, he is just lucky, right? So we need to explain, because every time something happens, you have to know why it's happening. Is it because you have a bug? Sometimes. Usually it is the case. But now it is not because we have a bug. There is a reasonable explanation, right? If we actually make our length perfect power of 2, it will return us the perfect thing. Of course, the problem does not arise when we are randomly shuffled, because then we are usually in the main part of the tree. By the way, let us do another experiment. We did it with reverse iota. Let us try it with iota. Anybody wants to tell me what will happen? Okay. The new one will work pretty well, guys. It's really, how come? So this astonishes some people. They say, so how come this is optimal and this is faster? Did we find out something? No, we actually didn't find anything. Optimal promises that it will do the smallest worst case number of comparisons, right? And it builds the complicated structure to assure that it never gets to a bad case. Here, this guy is just lucky, because after the first competition, the first game, the winner is never going to play. Everybody is going to be defeated by the runner-up. Right? Is it likely? No, it's very, very, very unlikely. What's the likelihood? Well, it's something like million factorial or something. So it's not going to happen, except practically speaking, of course. Inputs like that do happen. They're theoretically impossible, but happen in real life all the time, for both iota and reverse iota. Right? So we need to carefully see how it works. So you have an idea of how it all works? Okay, let us try to write it. So now, and probably we will try to do the following thing. I still want to see how you guys at least attempt to write it. If I modify the stuff now, could you not look at the, please do not cheat. So what I'm going to do is I'm going to go and how could I do it? No, not binary counter. Where it's this guy. By the way, I wanted before we do that, just wanted to show you something which is also very helpful. Remember, we made certain promises. We said we're going to use polylogarithmic storage. Remember that? So, by the way, now we validated number of comparisons. Now let us see what happens in terms of storage. Right? What I did, I assured that every time the algorithm is finished, we print the size of the pool, and equally, that when the algorithm is finished, we print the size of the counter. Right? So let us see what happens. Right? So counter size 20, plausible for a million. Yeah, that's what we should have. Pool size 175, which is, roughly speaking, half of 20 square. And that's, remember, it should be log n square over 2. That's our expected thing. So it's very good. It's very good. So again, to process million guys, we need 200 extra things of memory. That could be claimed constant space. Right? So I'm just showing how we validate that. And now let us attempt to write it. Or should I walk you through the code? Param, would you like to write it with me? Param is ready to write. Okay, so what we will do then, we will first, so all these files, all are here. Mean CPP is the main file. Algorithm contains iota, which we don't need to touch. List pool you should be familiar with. I modified it tiny little bit, but insignificant. Binary counter is also you're familiar. I modified it tiny little bit, but it's insignificant, and you could take a look. And min element, sort of, we started in the beginning what we have. In the beginning of this thing, we have the code as we basically had it the last time. We have combine class this operation and compare the reference. And then we have this code. So what we want to do, we want to modify this code starting at line 69 to deal, what was our first thing? We wanted to modify it so that use the random access iterators. Right? So let me just so Ahmed knows the beginning of the class. He doesn't need to bother with the little things. So what we're going to do, we're going to copy our this thing. Could you okay? Are you? Could you use my? Okay. So you just move 91 to 94 upstairs. Or give it to Jack. Jack knows Emacs. No, you don't trust Jack's knowledge of Emacs. What did you do? I copied 91. No. 91 and the whole signature, I meant, through 94. And copy it higher. Sorry. So now take these guys and put them upstairs. These guys. This from 91 to 96. Move it up to the above the blue line. Up, 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 up. Yes, right here. Okay. So, and let us help Param and put the code from the old min element 1, 2 into there, because he cannot possibly remember it.
You just copy the whole function.
Yeah. Yes. No, not this. That's the solution. No. Go up. No, not that. Let me control. Or at least let me show you. That was, guys, that was not very well engineered. That's the one. No, that's not the one. I apologize. That's yes, that's the one. Thank you. So let me just move the. It's 52 to 67 we need. So we do Control U 15. Is it 15? Control K, Control Y, and then we go to 74. And of course I forgot it should have been 16, not 15. So what is the first thing we need to do? That is true. What is the second thing we need to do?
So this is the algorithm where we are going to change min element when we are computing the second min to use the position, right? Using a random access iterator. That's what we are doing.
Yes.
Okay. So then nothing changes except the computation of min 2 at the very end.
Very good.
Let's scroll down to that point, and we'll see what's needed. Okay, so min element list is where that's happening, I believe.
Yes, that's where it's happening.
So what is min element list taking? It's taking a compare dereference thing. So
That's what should take? No.
I mean, so yeah, we need to modify that thing to do the other comparison, or we need to create a new type, maybe compare deref2 or compare deref stable. Okay.
We cannot use compare direct stable for the main type there because we're going to use it for something else in 5 minutes. So first of all, it just shows that we'll need to have another variable, and we will have to produce this variable here. So it's going to be something like, okay, you tell Ryan what it's going to be.
Well, we call it compare deref stable. Oh, compare deref stable type.
Okay, comp deref stable type. This is good.
Comp deref stable, open parent comp.
And then we need to go and do a type def.
Yeah, so we need to scroll up. Let's see.
So it should be, you should probably copy line 75.
Copy the whole thing and add stable.
No, but we still need the old one. Because we need both comparisons. We first do one comparison at the end, only at the end. Param was very careful. He said, only for the min list. Did you say that? You did. Control K. Or Shift down.
Alt W. Control Y. And now compare dereference table in both places. Oh, you already did?
No, no, he did it the first.
I see. Okay, and then we need to change the type.
Let's call it random access.
Yeah. Random access.
Okay. Do we need to do anything else here?
I don't think so.
So what do we need to do now?
Now we need to make a copy of compare dereference and call it compare dereference random access.
Yes. That's a good plan. Now, and you need to change some other name. The name of the class should be the name of the constructor. Otherwise, you get obscure and incomprehensible error message.
It says that it must return a type, and then you immediately know
What? He already did it.
He was doing it as you were talking. Maybe we change I to random access iterator or something, but
Or we actually just say / I is random access iterator. Whatever. Iterator of I. Yes, good. Now, that is tricky. So how do we do it? That's finally, prior to that, it was syntax. Now, little thinking is required.
yeah. So we can't just return this. We have to.
You cannot just return this. What do we comparison?
Then we do the reverse comparison, and if
I object. Why do I object?
is equality defined on this thing?
I object. Why do I object, guys? Comparisons are expensive. We do not want to increase the number of comparisons.
We need to somehow know that they're equal.
No, we don't.
We don't? Okay, so if star x is less than star y.
You're starting with the wrong thing.
Oh, first compare position.
First compare positions, because we somehow assume that that is free. Whether it's free or not, we do not quite know, but it's, it's the comparison on values which is very expensive. We made a promise we will not increase it. And the one which he was suggesting would increase it. And instead of doing 20, we will do 40.
And this a random access iterator guarantees that constant time anyway. So
And it's, well, the good model of random access iterator is what? Yeah, it's pointer comparison. It's not a big deal.
okay, so if x is less than y, then we return compare.
Here you have to think. That is a little tricky. Look at Bert. He clearly knows it's tricky. It's not tricky, but you have to think a little bit.
Okay, so what we want to do is we will need to return true if x is left of y and less.
But you already know that it's left. You already know that it's left. So what do you need to account for?
That means y must not be strictly less than x. That's what we need to check.
No.
X should win if x is less.
What happens if they're equal?
X wins.
How would you assure that?
Not star y, compare star y, star
Thank
x.
So you should not return compare, but the else. Now, in which case x, now x comes after y. When will it win? Only when it's really win. That's pretty good. She says we're done here. Okay, now, what I propose, instead of compiling and testing, let's go and compare it with what I wrote. Algorithm 0. Algorithm 0, no. Up. Use these things. Okay, I'll move around.
All right, it looks good.
All right, that makes me happy. All right? So there is a good chance your code is correct. And let us look at this part. It's exactly like whatever param dictated. Right? So this is called Vulkan mind melt. So, but in some sense, I'm very pleased.
It helps that we were pair programming here.
Yes. But, okay, guys, now what we do is we will attempt, would you like to continue?
So let me remember, algorithm 1 is...
Algorithm 1 is going to say we have forward iterators.
And we'll append, if this is the one with 2 lists, or this is the one with...
No. Well, algorithm, no, 1 is actually, this is, algorithm 1 is with 2 lists. There's algorithm 2, which we will algorithm 2 this. No, this is 1. This is 2. So the 2, the idea of 2 is add indices to iterators.
Oh, yeah. So actually, should we do that next?
That we should do next, but I sort of did them. Okay, let me tell you I decided to put the one with random access iterators last night. So today I came half an hour earlier and did it and compiled it and verified it. But I put it as 0 because my previous thing there was stable and stable 1. Now I introduce stable 0, whatever. It's a little bit.
So what should we do next? The one with the index?
I think that's the one we should do next.
Okay. Let's make another copy of the...
Actually, why don't we start with what you wrote?
Oh, just modify that. Okay.
And we could modify that because where was it? Stable. That was the one? No, this. That's it. So this is stable 0. So let us start thinking. First of all, I recommend reviewing things and figuring out what changes. Like, I recommend carefully looking at every type def.
The things we
the
put
same?
in the binary counter have to change. The pairs, I mean, they have to...
So what about list type?
List type. Wait, the first one is list pool, right? Oh, that's list type, yes.
Whatever, list pool. Yeah.
Before I do this, can I just say something so that...
You could say anything you like.
What we need to do here is we need to keep track of the iterator that reflects the min, the index of that iterator, and the associated list. Oh, sorry, wait a minute. No, anything in the list has to be a pair. Sorry. So, okay. So the things in the binary counter are the winner, and the things in the list are a pointer, the iterator, and an index. Okay.
Yes, that's how it looks.
So list type here is defined to be I and
But if that's what you do, how would you find out the index when you play?
that's a good point. So we need to keep the index of the winner around as well for that reason. Right. Anything that's in the list has to be the same thing that.
So in some sense, what it seems that happening, that what AWS services wish list, and this couldn't be mine. Or this is, do we see your? I could go wish. I'm not going to wish.
So I think anywhere we are talking about I, we need I and a number.
What is that number? I mean, what kind of a number is it going to be?
It's going to be the same thing as the type we give to our list pool, the n that we have for list pool.
But what the primary purpose of this number?
Oh, no, it's not going to be the same type. You're right. This is used to index into our original. Okay, right.
And what is the
Size t.
No.
No? Is there a way to get it from the iterator?
Yes.
I don't know how to get it from the iterator.
It's called a difference type of the iterator. Any range is encodable for a given iterator type. There is a type function called difference type.
Okay, so I : difference type.
No. That only in a good world that would be like so. Let me help you here. You cannot possibly know. This is, only C++ experts like John. John, would you lead us? How else? Because I might be a pointer type. You couldn't say insta : There is a specific type traits called, in the standard, Ahmed, iterator traits. Iterator affiliated functions could be obtained out of iterator traits. One day I will explain to you how it all works and why. Or maybe we will torture Bjarne when he comes. But in the meanwhile, let me help.
Okay, so maybe we define a new type.
Why don't we go all the way up and create new line 92. And we say type def. And here I'm going to say something awful, but you have to forgive me. We have to say type name, std, : iterator underscore traits, angle bracket, I bracket, angle bracket, : difference type. And we'll call it N, capital N, so that we never have to say that awful thing. Right? That's how, again, there is several things here. Let me just stop for a second. The deep thing is that mathematically there is a notion of a type function. A type could be affiliated with other type. The iterator type is affiliated with some integral type which measures distances through which this iterator goes. This is a mathematical concept. It's nothing to do with C++ or anything. It might exist even in Java if these people could conceive of such thing. But then comes the problem of how you could implement type functions in C++. And here comes the mumbo jumbo. Because basically what you suggested sounds a perfectly sensible thing. Say I : difference type. But I could be a pointer. And there is no way to get something into a pointer, to put a type def inside a pointer. So we need this complicated machinery of trait classes, which allows us to unify user-defined types and built-in types in terms of type functions. Right?
Yeah, I think it's best not to go into that.
Yeah. No, but eventually, you see, you might eventually observe that in your code, there are type functions too. Right? And then you need to know how to implement them today. Right? So,
Should we define a new type for that pair, or should we just do it twice?
Okay, honestly speaking, I do not remember how I did it, but I think I actually didn't define a type, but stuck a type right into std list pool, and in both places. I'll maybe define a type. Define a type, irrespective of what I did. I would put before line 94.
So second line.
93, second line.
Yeah, right after the difference type, we can define.
I would call it pair type, but std pair
I, comma n, greater than space pair type. And then in the line below it, replace I with pair type. No, not there.
that too.
That too, but in the definition of list pool. And let's see, counter operation type, we probably need to change that.
Yes, but we also need to think if any of our operations are going to work.
No.
Why?
Because the type of the thing changed.
How? We replaced I. You see, there are some things where we used I. Now we have pair there, so we'll probably need to do an extra
Some kind of adapter or something
dot
like
first.
star x dot first instead of just star x.
Okay, why don't we go eat food? And then we will do, I think we're well on the way of actually